Okay, so we are going to start today's class, and so in today's class, I'm going to be shuffling between the PowerPoint presentation and Blackboard. So today we are going to start linear ODE of higher order. Linear ODE of higher order. Okay. So before I start, let me tell you that in your syllabus, so there is something called Groundworks Inequality. Okay. As I have mentioned earlier, this Groundworks Inequality it is used as a lemma to prove uniqueness theorem. Since we are not using it in our proof of uniqueness theorem, so I'm not going to discuss in detail about this Groundworks inequality. They are just simply mechanical. I mean, two sets of inequalities are there, although they are the same inequalities, but they are put in two different forms. So what I'm going to do, I'm going to upload my notes on Groundworks inequality. I've scanned it and uploaded. Okay, so you can follow it. So maybe later on, when we are going to discuss system of linear equations, and when we are going to convert the set of differential equations into some matrix equation, so I may use Groundworks inequality there. Okay, fine. So let us get back to linear ODE of higher order. Okay, so let us consider the nth order ODE. Nth order ODE, of course, here y is the dependent variable and x is the independent variable. Say, suppose my suppose this is something like g of x. Okay, and if I want to use this as an initial value problem, so then this being an nth order differential equation, so it must come with some n given conditions. Okay, so let us consider a point. Let us consider a point x naught in the interval of definition of this differential equation. Okay, so then I'm going to consider this differential equation your subject to the conditions, your y x naught equal to, let us call it y naught, y prime x naught equal to say y1, and in this way the n minus 1th derivative at the point x naught, let be y n minus 1. So what we have done, we have simply given the statement for an nth order differential equation. Okay, so what I'm going to do, and later on you are going to see that I'm going to concentrate more on the second order differential equation, right? More on second order differential equation. And again, I'm not going to discuss anything about the solution techniques because you have already learned them in your BSc and MSc. Okay, so I'm going to concentrate more on the nature of the solutions. Okay, and probably I'm going to deal with how to find solution with the method of variation of parameters. That I'm going to do. But other techniques, like linear equation with constant coefficients, all this stuff I'm not going to discuss. Okay, fine. So now you are already aware of the existence and uniqueness theorem for a first order differential equation. To be precise, first order ordinary differential equation, right? Okay, so it came with only one prescribed, initial condition. Now, this being an nth order differential equation, so it has come up with your n given conditions, okay? And as you know, we are going to designate this point x naught in some interval AB as my initial point, okay? So now you may be pondering, what is going to guarantee? What is going to guarantee the uniqueness and existence of a solution, of the differential equation given by 1 or of the initial wave problem given by the nth order differential equation 1. So that we are going to discuss. So uniqueness and existence theorem for nth order differential equation, and it is pretty straightforward. Let me tell you what it is. Like I said, and of course, here remember these all the coefficients of the derivatives. Of course, this y also I can describe it as the zeroth order derivative, right? Okay, so all of them, they are nothing but functions of x. They are nothing but functions of x. Okay. So now you can see that here all the derivatives are that being considered here. They are simply in the linear form. Okay. They are simply in the linear form. Okay. And I'm not considering the dependent variable coming into all these coefficients. Okay, so basically I have considered here a linear nth order differential equation. Okay, fine. So now what is the uniqueness and existence for this? Can anybody tell me if you have already studied it? Do you recall it? Yes? Does anybody recall it? Okay, fine. Am I audible?
Yes, sir.
Yes. Okay. Yes, sir. Sometimes, when you guys are silent, it seems that I'm talking to myself in an empty room with no people present here. Okay. So you will see that those conditions for uniqueness and existence, they are pretty much straightforward. So what it is, it simply says that all these functions, your a naught up to an together with this right hand side, this g, all of them, they have to be continuous in the interval a comma b. Okay, so then this equation 1 under this respect condition, it has a unique solution. Okay, so now let me just simply show you the slide so that I don't miss anything. So this is what it is. I have already told you that. So this I have already described. This one I have already described. Okay, the equation number 1 and subject to all those conditions, and they are talking about an interval I, which I can take as a which I can take as a closed interval a comma b. Okay, so now let me see this existence and uniqueness. So this is the existence and uniqueness theorem for this one, for the nth order ODE. So what it says, as I have told you, that if all the coefficients of the derivatives as a function of x on the right hand side, and again another important thing I forgot to tell you, that the coefficient of the nth order derivative, that is a and x, it has to be non-zero. Okay, and later on, even when it is not stated, we are going to assume that it is non-zero. Okay, fine. So now let me come to this problem. Let me come to this problem that you can see that is written there. So it's a pretty straightforward equation. It's a pretty straightforward equation. So what it is 3y triple prime plus 5y double prime minus y prime plus 7y equal to 0. And of course, I mean, it has come up with so how many like say initial condition I will require?
Three initial conditions.
3 initial conditions. Okay. Okay, fine. So let me give you these 3 initial conditions. Okay, fine. Now, obviously, here, what are the coefficients? Here the coefficients, here say a3x, this is equal to 3, a2x equal to 5, a1x equal to -1, right? a0x equal to 7, and gx equal to 0. Fine? Isn't it? Right? And they're all continuous functions, I mean, in any interval containing 0. Fine? Okay? So, now, you know that this being a homogeneous equation, so y equal to 0 is always going to be a trivial solution. Is it okay?
Yes, sir.
Yes?
Yes,
so,
sir.
by existence and uniqueness theorem that we have just described, so what must happen? What must happen then?
It has only one solution, which is the zero solution.
Exactly. So y equal to 0 is the only solution. That's it. Okay. So and what about this one? Like the second one? See again in the second one, you can easily verify. You can clearly see the slides, right? Yes.
Yes, sir.
Yes.
Okay.
Yes.
Fine. So in the second one, if you look at that, and again in blue, I have an expression y equal to cx squared plus x plus 3. Okay. So if you plug that in, you can see that. I mean, that is going to be a solution. You can easily verify that. Okay. So now, what can you say about that then? Yes.
So there will be infinite number of solutions.
There will be an infinite number of
There will
solutions.
be infinite number of solutions.
There will be an infinite number of solutions. I mean, okay. So can you tell me from where do you get that conclusion from?
Sorry, sir.
From where did you get that conclusion?
If you take
Say.
this x equals to 0, then this x0 is vanishing the arbitrary constant. So there is no effect of this arbitrary constant.
Exactly.
So this arbitrary constant will alive every time.
Yes. And again, see, from the equation, we can see that whatever value of the parameter you are going to assign to C, right? It is going to give you that many solutions, isn't it? Right? And all of them are going to be solutions. And here, basically, the answer lies on these being 0. Answer lies on this being 0. So this is a prerequisite that a and x cannot be equal to 0. Okay, I am again going to come back to something like this later on when I am going to discuss about power solutions. Okay, fine. So now let me come to, okay, fine. So these boundary value problems I have again earlier. What I did, so maybe I will just hide it for the time being. Okay, fine. So now let me make the distinction between. So now I'll be discussing a second order ODE. Okay, I'm going to discuss a second order ODE. Okay, fine. Here. So now suppose my ODE is given by this one. Simply, I can do something like this. Okay, now that's y. So suppose this is equal to g1x. Should I? Okay, I can make the same. Okay, fine. So now I may have something like your yx not equal to y naught. Okay, then y prime x not equal to y1. Well, definitely this y naught, sorry, x naught is a point in the interval of definition. Okay, fine. Now, interval of definition says that was I. That was I. So let me call this. Let me call this as equation number 1. Okay. So now let me make the demarcation. Okay. Say suppose I am considering a sub-interval a comma b in my interval of definition I. Okay, fine. So now instead of this, let me impose the conditions. Let me impose the condition y at a. This is equal to say y1 and y at b equal to say y2. Okay. See, basically what is happening? You know that in order to solve an nth order differential equation completely, what we must have n at least n prescribed conditions, right? Fine. So here, see here also I have two conditions. Here also I have two conditions for the second order differential equation. So definitely I can completely solve the given differential equation 1. Is it okay? Fine.
Yes.
Yes. Fine. So now, if you recall, so what was the say, suppose this is my interval I, okay, this is x naught. I can still consider a b here. So so the physical interpretation was this, that I mean this is my what? This is my point your x naught y naught, right? Okay, and what happened at the point x naught y naught? At the point x naught y naught, the slope of the tangent to the curve yx, it was given by the value y1. Okay, fine. So now in this particular case, what is going to happen? Say, suppose this is my A, this is my B. Okay. So what it is telling me, that if say this length is y1, and suppose this length is y2, then what happens? Basically, my solution curve passes through those two points. Is it okay with everybody?
Yes, sir.
Right? Okay. So physically, what it describes, say this is nothing but the description of an initial value problem. Okay, and this is the description of a bounded value problem. Is it okay?
Yes, sir.
Fine.
Yes, sir.
So you and again see, it is not necessary that you are going to have unique solution for both of them. Okay. So basically, what must happen? say you may have another curve passing through this, only with the condition that the tangent at the point, right? They are going to coincide, right? The slope of the tangent is going to give you the same value. That's it. And here also, here also, I may have, another solution like that. I may have another solution like this also. Is it okay? Fine. So the first here these conditions describe the second order differential equation as an initial value problem, and this one as a boundary value problem. Okay, fine. Is it okay with everybody?
Yes, sir.
Right? Okay.
Yes, sir.
Fine. So just let me show you this slide. So this is what I have already told you, that the prescribed values ya equal to y naught and yb equal to y. Okay, here they are using y naught and y1. Don't worry about it. I was using y1 and y2. You don't need to worry about it. And a solution of the foregoing problem is a function satisfying the differential equation on some interval I in such a way that obviously I must contain a and b, and the graph of the solution, it passes through the point. In my case, the way I have drawn it is a comma y1 and b comma y2. Okay, so now again, the thing is that one thing you should remember is that you shouldn't think that in case of the boundary value problem, the boundary conditions are only going to be defined in this way. It is not necessarily so. Okay, fine. So it can be given in terms of the derivative of the function at some points as well. Okay, so now I'll just spend some time on this. Okay, so now your boundary condition may be something like this: your y prime a equal to y1 and y prime b equal to y2. It may be something like that. I mean, apart from this, I'm talking about possible boundary conditions, and okay, it may be fine. Okay, and it may be some combination of both of them. It may be something like your alpha 1 ya plus beta 1 your y prime b. This is equal to, say, gamma 1, and something like it may be, or maybe because I'm using y1 and y2, let me stop y1, and then alpha 2 y prime a plus beta 2 yb is equal to y2. Okay, fine. So now if you have a boundary condition like this, we say that it is what? To forget everything. What?
It's a boundary value problem.
No. The problem is boundary value problem, but those specific kind of boundary condition, what is it called?
Actually, boundary conditions.
Something Dirichlet conditions.
Dirichlet boundary conditions. Okay, fine. And these are examples of. So whenever at a prescribed boundary you have the boundary condition given in terms of the derivative. See, I am simply using the term derivative here, but I'm going to change that. Okay, I'm going to change that slightly later on, because this is only a function of only one variable only. Okay, so derivative means derivative with respect to the independent variable, right? So if you have a boundary condition where you have, boundary condition given in terms of the derivative of the function at those points, okay, we call it Neumann. It is not pronounced as Newman. It is Neumann boundary condition. Okay, and if they are combination of both, then we say that it is mixed. It is called mixed or your Robin. Mixed or Robin boundary conditions. Okay, fine. See, and this is pretty. You may be thinking. I mean, and again, this is not only for simply academic purpose, right? These are physical significance also. Say, suppose I am considering iron bar, say, which can be represented by simply a interval like this. Say I am taking an iron bar of length 1. Okay, and suppose I have a differential equation by solving which I can. I'm able to know. I'm able to know the temperature distribution along this rod. Okay, fine. So then what may happen? I may impose, and you may be thinking that, okay, like what was happening? Like you have you are just taking out the rod from somewhere, okay, and then suppose you are heating here at 100 degrees Celsius, and you are dipping this in ice cold water. Say suppose it is 0 degrees Celsius, right? So then these kind of conditions, it is going to represent your Dirichlet boundary condition. Okay, fine. And it may so happen that at one end, you are maintaining it at fixed temperature. Okay, but at the other end, what you have done, you have given some insulation there. You have given some insulation at the other end, so that no heat can exit or enter. Okay, so in that case, you are going to come up with something like this. Okay, if my variable y represents the temperature here, so if it is insulated, so this will be simply 0. Okay, and if it is a combination of, say, there is some effect of radiation also, then you may come across this kind of boundary conditions. So all these boundary conditions that are being discussed about, it like say, it hasn't come from, I mean, nowhere. It has some physical significance. Okay, so now I told you that here, while describing the Norman boundary condition, I was just mentioning about derivative. Okay, see, whenever we talk about Norman boundary condition, although we are here, since we are dealing with ordinary differential equation, that is why I am simply uttering the word derivative. But in fact, it is not only derivative, it is the normal derivative. Okay, so like suppose I am considering a two-dimensional problem. So then what is going to happen? Like here, then in that case you are going to have more than one direction, isn't it? More than one variable. Fine? Are you getting the point or not? See here, this is an ordinary differential equation I am dealing with. So that is why I simply have, only one independent variable, isn't it? Fine?
Yes.
Yes?
Yes, sir.
But in case of, more than one variable, you are going to have two. So in that case, what is going to happen? Say here, suppose the iron bar is like this. Okay. So then, suppose it is like this. So then, if I consider these two ends, okay, the direction normal to these ends is always something like where the arrowheads are. Okay, so basically it is simply x direction, right? So when I am considering an ordinary differential equation, so here what I am doing, so direction normal is simply x. Although these two are points, I am in fact assuming that there are some vertical line passing through those points, and I am imposing the boundary condition in such a way that the normal boundary condition is nothing but in terms of the derivative with respect to x. Okay, so now had I considered this bar to be a two-dimensional region, then if I impose, I mean, in this rectangular, see, again, remember, whenever you consider a domain, like, so that domain, I mean, that domain, in that domain, we are going to solve the differential equation, right? So that domain doesn't necessarily have to be like beautiful like this, your rectangle. It can have arbitrary shape, okay? So in case of this rectangle, okay, so now suppose I am considering a function phi of x, y. So then here, on the top boundary, if I consider the normal direction, it will be in this direction or these directions. Okay? So then what I have to do? I have to consider del phi, del y. So this is going to constitute some normal boundary condition in that case. Okay? So in case your, suppose I have an arbitrary domain, right? So then I have to do like this. So these are my normal directions. So in that case, I am going to use simply del phi, del n, where n is the normal direction to the boundary of the domain at that particular point. Now, is it clear what is normal boundary condition? The physical significance of it.
Yes, sir.
Right? Okay. You just shouldn't try to, I mean, go through things like mechanically, like say, okay, it is simply derivative is that, and I can easily solve the solution and fine. It shouldn't be like that. Okay. Fine. So now. Let me again show you these slides. So this is what this is what all the type of boundary condition they have been described here. Okay. So now there is an interesting thing there. So can you see that? Yeah, can you find me the solution of that? Oh, it is already given, so it is even easier for you. It is even easier for you. Okay, so now what it says that a boundary value problem can have no solution, an infinite number of solution, or what? Only one solution. Okay, and they have given what? 16 x equal to 0. Okay, fine. They have given this. Okay, fine. So you already know, I mean, linear equation with constant coefficients. Fine. D square plus 4 square equal to 0, auxiliary equation. So eventually you are going to get yx to be equal to c1. No, this is a function in sorry. They have given in terms of x, sorry, xt. I'm assuming that x is a function of t. Okay, so c2 sine 4t, right? Yes or no? Is this the solution?
Yes, sir.
Yes. Okay. So now, suppose I impose the boundary conditions like this. Okay, fine. So then, if I plug in x0 equal to 0, this is going to give me what? This is going to give me
C1 equals to 0.
C1 equal to 0, right? C1 equal to 0. So my solution will be something like 40. Fine. So now, if I want to plug this in, then what is going to happen? At the point t equal to pi by 2, if I try to impose this boundary condition here, so what is going to happen?
For any C2, it is true.
Yes.
For any C2, it is true.
For any C2, it is going to be true. Is it okay?
Yes, sir.
Fine?
Yes, sir.
Isn't it? So under this prescribed boundary condition, what you can have an infinite number of solutions. Is it okay? Isn't it? Whatever value of C2 you plug in here, right? It is always going to satisfy this boundary value problem under these prescribed boundary conditions. Is it fine? Okay. So now what about this?
Only zero solution.
It
Zero
has,
solution.
yeah, it has only the zero solution as the only solution. Is it okay with everybody? Right? See,
Yes, sir.
Yes, sir.
obviously, if your this is your boundary condition on the left side. This is your boundary condition in your left. Your equation, sorry, the solution is always going to be of this type. Okay, fine. So then, if you plug in t equal to pi by 8, so this is sine pi by 2, it is equal to 1. So C2 it will be equal to 0, right? So your x equal to 0 will be the only solution. And what about this guy? Yes.
No solution.
No solution.
No solution, right? Because my solution is always going to be of this type because I am plugging in x0 equal to 0. So now if you plug that in, there, your left hand side is going to give you 1 and right hand side is going to give you 0, right? That is an absurdity. So under this boundary condition, you cannot get a solution to that differential equation. Is it okay? So that means a boundary value problem can have infinite number of solutions, no solutions, or only one solution. So here you will see, okay, fine. So and this in the figure you can see the solutions corresponding to the first boundary conditions where there were infinite number of solutions. So you can see that for different values of C2, you can have different solutions. Of course, they are passing through this point 0 and pi by 2. I mean t equal to 0 and pi by 2. So now can you see the question there? Does it contradict theorem 4.1.1? 4.1.1 that was nothing but the uniqueness and existence theorem for an nth order differential equation. Does it contradict it?
But sir, this was the initial value problem, but this is the boundary value problem.
Yes, that is the answer. See, earlier the theorem, the conditions were given in terms of derivative up to n minus 1th order. Is it okay? That was an initial value problem. Okay, later on, I mean, in some more interview, job interviews or something like that, you may come across these kind of questions. Okay, fine. Hopefully, you'll be able to answer that. Okay, fine. So let me see what is next. Okay, fine. So this also you already know. So if you look at the slide, then I was discussing about equation number 7, right? I was discussing about equation 7. So now in equation 7, if you plug in the right hand side to be equal to 0, right? So then the resulting equation, differential equation, we say that it is a homogeneous equation. And in case gx not equal to 0, we say that it is a non-homogeneous or inhomogeneous equation. Okay, fine. And there are 2 examples I'm given here. Like, and this is pretty straightforward. Like here it is 0, and here it is for x. And you know that for any value of x, here it is for x is never going to vanish. Okay, fine. So, and again, say this one was in some other context. The word homogeneous in this context doesn't refer to coefficients that are homogeneous function. You have to remember that, because earlier, say if when you were studying, like say variable separable type first order equation. So then you must have recalled that you had something like that they had they were called homogeneous when if the coefficients of the differentials, they were homogeneous in their powers. Okay, so this is not about that. This is homogeneous is about the right hand side being 0. That's it. Okay, fine. And this node, I mean, this is already I have told you, like say, to avoid needless repetition throughout the remainder of the course, what we are going to do, we are going to make the following important assumptions that what we are going to do on some common interval I, we are always going to assume, if nothing is stated, that all the coefficient functions they are continuous in the prescribed interval, and of course the very first coefficient, that coefficient of the nth order derivative, that is not equal to 0. Okay, fine. So now let me come to linear operators. So because that is going to be important. Just a minute. Okay. See, today's class is basically going to be like some kind of recap, whatever you have done earlier. But I'd like to throw some more lights on whatever you have studied. Okay, right. So this one, I'll now come to your differential operators. Okay, fine. See, suppose I'm considering this differential equation. Dy dx2 plus 3 dy dx plus like 2y equal to say incorrect, something like this. Okay, fine. So now what I can do, like say the ddx, I can define it as an operator d. Okay, so that means your dy dx, I'm going to write it as g1. Okay, and then d2y dx2. Again, if I write in terms of operators, so this is dy dx. Okay, so ddx, I can write it as d of dy. Okay, this is d square y, and so on. Okay, so basically, I could have written this. I could have written this equation simply as d square plus 3d plus 2y equal to e to the power x. Is it okay? Fine.
Yes, sir.
Okay. Yes. So now, what is going to happen? Like I may write this operator as something like L of D. Okay, fine. Now any operator like this, or in short, you can also write it as, Ly equal to e power x, where this L has been defined in this way. L of D is this. Okay, fine. So now from linear algebra, you know that an operator of the type L, I mean, it is going to be called a linear operator if you have something like this. Say, earlier I had something like alpha x, beta y. So this is fine, something like this. Okay, The linearity you would have proved like this, okay? But now here, because I am using your y as my dependent variable and x as my independent variable. So here, in order to prove the linearity of the operators, so what you have to do, like L, it will be what? Alpha, I'm going to take two functions. Okay, so if you can get something like L fx plus, so then the linearity will be proved. Is it okay? Fine. You already know it. Isn't it?
Yes, sir.
You already know it. Okay. So now let me get back to these slides again. So here there's a question. Say here I was talking about whether L is linear or not. So like whatever examples so far I have taken, definitely L was linear. Okay. So now for nth order differential operator, as I have told you earlier, see all the coefficients I have taken them as constants, right? So if they are not constants, so they are going to be functions of x. The way we have taken equation number 1 in our original nth order linear differential equation, right? So if I define the operator as the expression in equation A, so then what is going to happen? You can easily verify that L is a linear operator. Is it okay with everybody? Fine? Yes?
Yes, sir. Yes, sir.
Yes. Okay, fine. So now let us come to the superposition principle here. And again, see, so far I am discussing all my terms here for an nth order linear differential equation. Okay, an nth order linear differential equation. But most of the proofs, what I am going to do, I am going to specifically deal with your second order differential equation, and I am going to do the proofs for that. But so far, you will see that in all the slides, at the beginning, you are going to see only the general statements. Okay, so now this theorem 4.1.2, it is superposition principle. You already know that if y1, y2, yk are they are solutions of the homogeneous nth order differential equation 6. So basically that original nth order differential equation with the right hand side being 0. So then their linear combination is also a solution. You know that this is nothing but method of superposition. And here, interestingly, we still haven't talked anything about the solutions being, linearly dependent or independent. I'll come to that later on. Okay. So, and again, these are obvious. A constant multiple. And you don't need to worry about this, that I haven't proved anything here. I'm going to do everything for, second order equation. Don't worry about that. Okay. And a constant multiple of a solution of a homogeneous equation is again a solution, right? And again, this is very important. Homogeneous linear differential equation always possesses the trivial solution y equal to 0. Right? So now again in the example 4, what you can see that you can easily verify that these two are solutions of the given differential equation. Okay, fine. And then what is going to happen? So any linear combination of them is also going to be a solution. That is nothing but the method of superposition. Okay, fine. So now let me come to linear independence and dependence. Okay, so you have already gone through this. But I'll just show you some examples, some graph of some examples later on. So linear dependence and independence. Okay. You already know. So say suppose I am considering n functions. Okay, right? Of course, their functions are real variable. Okay, well, I mean x has been defined in some interval, say a b. Okay, fine. So then, I mean, they are called linearly independent if there exists. If there exists, I mean scalars C1, C2 up to Cn such that this equation always implies that all those Ci they are 0 for all I going from 1 to n. Okay. Similarly, they are called this set of functions. They will be called linearly dependent if what this expression is satisfied. Yes, with at least
For at least one non-zero. For at least one non-zero
Ci
Ci.
for some variable I lying between 1 to n. Okay, so now you may be asking me why I am choosing these functions, why I am choosing some functions here, and why I am talking about linear independence and dependence. Okay, I have chosen n functions. You can see here. Okay, so why I am choosing these functions? Because eventually I am going to consider those functions as the solution of some given differential equation. Is it okay? Fine. It is not merely like say from the linear algebra point of view. Okay, fine. So you already know this. What else? So now, okay, fine. Something like this. Okay, fine. This is a graph of what?
Sin x.
Yes,
Sin x.
sin x. Now I am going to ask. How do you know this is sin x? Exactly sin x.
Maybe 2 sin x, 3 sin x, like y equal to k sin x.
Okay. Suppose this point is say 1/3, then the graph is of what?
Sin x by 3. 1/3 into sin x.
Yes. See, I didn't say anything about the amplitude. I intentionally drew it like that because see the physical understanding you should always have. So only when I'm going to mark it, then I'll be able to say, I mean, exactly what is the amplitude, right? Okay, fine. So now, say, okay, for the sake of simplicity, let me simply designate it as 1, and let me designate this point as something like say C not equal to 0. Okay, fine. So then, what is going to happen? What is going to happen? Like I am going to have, isn't it? I am going to have this as y equal to c sine x. Is it okay?
Yes.
Yes, sir.
Yes, sir.
Yes, isn't it? So, what is it telling you? What is it telling you? Like, what is happening here? You can see that if I call it as y1x, this is y2x, okay? Say, suppose this is y2x, this is y1x. So, we have seen that one function is the scalar multiple of the other. Is it okay? Fine. So this gives you a pictorial description of two linearly dependent functions. Okay? Fine. So I'm going to pose you some questions here. So this is what it is. This is what it is. I have just graphed and something like that. Something like that. The first one was first one was a sine 2x. And the second one was simply sine x cos x. And you know that sine 2x is 2 sine x cos x. Okay. So the second one has been derived from the first one by simply multiplying it by half. Is it okay? So here you can see that the amplitude of the green curves, it is half, and amplitude of the red curves, it is 1. Is it okay? Fine. So now you can see, two graphs here in figures A and B. So can you tell me whether these two functions, f1 and f2, they are linearly independent or dependent?
They are linearly independent.
Linearly independent. Okay.
Yes.
Suppose. Okay. Yes. If I had taken the my interval from negative infinity to 0, what would have happened? Say suppose I was considering only the interval from negative infinity to 0. Then
Then they will be
then they will be linearly
dependent.
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 Yes, because one is going to be the negative of the other, right?
Yes, sir.
Right? It is clear with everybody, I guess. They say my situation was something like this. Say I had something like this, and then I had something like this. I had something like this. Okay, fine. So then this was mod x, right? This was mod x, and this one was y equal to x. Okay, fine. And it was considered in the whole interval negative infinity to infinity. Okay, so now had I curtailed it from simply negative infinity to 0, the situation would have looked like this. Okay, so then you can see that this can be obtained from this simply by multiplying the value of the function by negative 1. Okay, so they are going to be linearly dependent. Okay, so I have some more interesting questions here. This one, the first example. Now I am giving you 4 functions. Yes.
Linearly dependent.
Sin square x, cos square x, tan square x, and sec square x. Are they linearly dependent or independent? On the interval negative pi by 2 to pi by 2.
Dependent.
Dependent. Why?
Dependent.
Because
So sec square x equal to sin square x plus cos square x plus tan square x.
Okay. So yeah, basically what is going to happen, I can have sine square plus cos square x plus tan square x minus sec square x to be 0, isn't it? Yes?
Yes, sir.
Fine. Just let me just write it down something. I'll come back to you. Okay. Okay. Fine. See here. So coefficient 1, coefficient 1, coefficient 1, and plus coefficient minus 1. Right? So I have been able to find, I mean, what? Arbitrary constant C1, C2, C3, C4, not all 0, in such a way that this relation is giving me a value 0. Is it okay? Fine. So what about this? What about this? F1x is this. This is x minus 1. So are they linearly independent or dependent?
Dependent.
Dependent. Why?
F1
Why?
plus F2 minus 5 F3 plus 0 F4 equals to 0.
Okay. Yeah, definitely you'll be able to find a combination. You'll be able to find a combination which is going to give you. No, what, yeah, x square you can always make it 0, right?
Yes, sir.
Yes, sir.
Right? The coefficient you take is 0. When that is the yeah, that is the, I mean, simplest thing. Okay, so now I think how much time do I have? Okay, so I would like to discuss, I mean, one example that in yesterday's class somebody told me what an interesting example. So let me spend a few minutes on that, and then I will come back to, I mean, couple of answers that you guys have written in your quiz, where I would like you to be more specific in future on that. Okay. This was, sorry. I'm still not going to write anything here. Okay? Can everybody see the differential equation? Fine?
Yes, sir.
Right? So the right hand side, that f of xy. Xy to the power half. So obviously this is continuous throughout the whole R2. Right? Okay? Throughout the whole R2. And then, like, if you take its derivative with respect to y, so it gives you, right? Okay?
Yes, sir.
Right? That makes it, I mean, that makes it not continuous in any region where y equal to 0 belongs to, right? Okay, so that is why, like say Picard's uniqueness condition, I mean, it fails in any rectangular domain containing the point x naught y naught such that y not equal to 0. Fine? Is it okay? Fine?
Yes, sir.
So that is why I should avoid this initial condition, right, in order to get a unique solution. If I want to get a unique solution, I am going to avoid that. Is it okay? Fine?
Yes.
So, and what we did, like we have already figured out that y equal to x squared by 4. This gives you one parameter family of solutions. Is it okay? Fine. So then, yesterday, yeah. So yeah, can you tell me? I mean, who told me this about this problem yesterday?
Sir, I am.
What's your name?
My name is Balasubramanian.
Yes.
Sir.
Balasubramanian.
Yes.
Okay. Yeah. Okay. See, this is a very interesting. Now I am very interesting situation. Okay. Fine. So he said that definitely x to the power 4 by 16 and y equal to your x squared by 4 minus 2 whole square. Both are solutions to the initial value problem given by this.
The second one is not a solution of this initial value problem.
Which one?
Second equation, y equals to x squared by 4 minus 2 whole square.
Why?
This is not because
Tell me why.
if you differentiate this with respect to x one time, then y dash equals to x into in the bracket x squared by 4 minus 2. But this x squared by 4 minus 2, this term is negative, minus root y in the interval of 2 root 2 minus 2 root 2 comma 2 root 2 in the open interval.
Okay, I got it. No, but see, if I go by this solution, right? If I go by this solution, isn't it? I can always verify that, okay, because I am going by this solution. I mean, whether you plug there in or not, this should be a solution. This should be a solution, isn't it? I'll stop you there. What I'm going to tell everybody that what mistake we do. Okay, what mistake we do. Okay, like here definitely, like say if we like simply have a glance at this. Obviously, this has come from here. This has come from here. Because what is happening here, don't interrupt me for the timing. I'm going to give you enough scope to interrupt me later on. Say now, suppose I'm plugging in this initial condition here, So then, if I plug this initial condition here, that is going to give me y equal to your, this is 1 plus c. Fine? Okay? So this should have given me 1 plus c equal to plus minus 1. 1 plus c equal to plus minus 1. And from there, I have got c equal to minus 2 and c equal to 0. Fine? And that would have given me these two solutions. Yes? Now you can interrupt me. Yes? Yes or no? Like,
Yes, sir.
our very first, instinct is to find out the constant c, isn't it? Right? Finding out the constant c, right? And like if we go by our instinct, and then I have found out that I have got two constants, and it is giving me two solutions, and oh my God, like Picard's uniqueness condition, despite it satisfying it, my sufficient condition is also not enough to give me a unique solution. Okay, so coming back to Balasubramanian's point, even without verifying this being a solution, I want you to concentrate on this function. Okay, and again, I think 3 or 4 of you, you have given a standard answer to question number 2 in my quiz. Like you are saying that y prime equal to square root y plus 1, and I think y0 equal to 0. This has a unique solution despite not satisfying your Picard's condition or that Lipschitz condition, right? Okay. See, whenever we have a function like this, whenever we have a function like this or this, this. So what is happening now? Say, suppose I plug in y equal to 1, right? Plug in y equal to 1. So I can get two values, isn't it? Square root y. It can be -1 and 1. Isn't it? Is it okay with everybody?
Please,
Fine.
so please repeat again.
Right? So
The
in
last
that
line, please
case,
repeat again.
the definition of a function is going to fail. Isn't it? If I consider this as a function of y, fy equal to simply square root y, right? For the same value of y, or maybe say phi of x equal to square root x. So if I consider like for the same value of 1, I am getting two different values of phi of x, which doesn't define me a function, right? So why it is so? Why this is still a function? Or why this is still a function? Because it is a convention. It is a convention that this takes care of only the positive square root of x. Obviously, while defining this function, I am going to define only define this only in the interval 0 infinity. Is it okay with everybody?
Yes, sir.
Right?
Yes, sir.
So by a similar argument, for this function, it must be defined in a open rectangle or rectangle whatsoever. Open rectangle, definitely. In an open rectangle where I can choose only this one. Just a minute.
Y
Yeah.
greater than 0.
I can choose only this interval for y initially. Okay, I have already seen that y equal to 0, highlights this one, but my original function, in order for this to be a function, I have to define this in this interval for y. Okay, fine. And then the next thing is that I am always going to assume that this one I am taking the positive square root. Is it okay? Only then that is going to be a function. Is it okay with everybody? Right?
Yes, sir.
If that is so, here when you are going to plug in y equal to 1, right? If I go by the usual convention, then this is going to allow you to take only the positive square root, and that is going to give you only one solution. Is it okay with everybody? Fine. The confusion arises because of that. Is it okay?
So please
Because
repeat
it's
again.
silent. The confusion
Please
arises
repeat the
because of
last
say,
So please
yes.
repeat the last part. Please repeat the last part, last few lines.
Last part. Oh, you want me to repeat the last part, right? Okay. So I have already told you the convention that whenever I write a function like this or function like this, I am assuming that I am taking only the positive square root of x. Okay, right? So then only it is going to define me a function, right? So if I want negative square root of x, I just simply define my function as pi 2x to be equal to something like this. Okay, so that means if you want to define this as a function, you must assume that you must be under that convention that here I am going to consider only positive square root of y. Is it okay? Fine. So if I am going to assume that, so then for this solution, for these solutions to be valid for this function, when I am going to plug in this initial condition, see, this initial condition gives me this, because this value, it belongs to y, right? This value belongs to y. So whenever I am going to consider square root of this, I am going to consider only the positive square root for this equation. Okay, I have taken negative square root in this equation. Had I taken, this to be x into this minus square root y, this something like this. Okay, so then I would have been allowed the negative square root, but only one at a time. Okay, so that is why you cannot say that it violates the conditions of Picard theorem. No, they are two different solutions. So that if this is one, okay. So I'm simply going to take, if this is one, like I get this solution. If this is -2, I get this solution. So like say for this one, only this is going to be better. Is it okay? Fine. And for that matter, yesterday I was asking you, like, I think 3 or 4 they have taken this one. They have taken this one. But again, like say you simply memorized it from some of your earlier, practice or something like that. You replicated it. You didn't give me the, explanations clearly there. Okay. So eventually, what you did, you prove something like gx then square root. This is y1x, y2x less than equal to 0, right? So you got something like that. That gives your function to be monotonically decreasing. So over there, I had this doubt. Why because I already know that gx is greater than 0. And now my next confusion was why this is always going to give me positive value. This is going to give me positive value only under that kind of assumption. Okay, but anyway, that is a convention. I'm not worried about it. But all of you, whoever has attempted to answer question 2 like that, you didn't give me complete explanation for this being negative. Okay, and after that, why monotonically decreasing that particular property leads you to 0 as the only solution. That thing also you have described clearly. Okay, fine. So anyway, I think I'll be ready to hand you over your answer script. Tomorrow probably. Yeah, I'm still reworking on that. Whether I can increase your marks, okay? I'm just looking into this, or maybe decrease your marks. Hopefully that is not going to happen. Okay. So I will then see you tomorrow, right? At 12.
Hello, sir. Hello, sir.
Yeah, I'm listening. You can ask.